Welcome back to the series, everyone. This is a bonus episode because last time, although we left Talos running code, it was kind of bare, it didn't have a case, and it's going to the Dutch Home Computer Museum, so it needs to have a case. That's what I set out to do. I have used cut to size transparent acrylic plates because we need to see the LEDs through the case. It needs to be transparent. And I glued them together using whatever I had available to me in the art atelier of my girlfriend downstairs. I taped everything together with the proper glue. I used masking tape to keep it clean and neat. And once I've removed all the protections, all the tape, all the film, we got these beautiful transparent case that will allow users to see all the LEDs in Talos. And when I put it all together, this was the result. Beautiful, huh? Notice that there is a base plate also made of acrylic underneath the motherboard, the horizontal board at the bottom. It has matching holes to that of the motherboard, so I could bolt the motherboard to the base plate at the bottom, which has some rubber feet glued to it as well. And then I just put the lid, the cover, on top. It's very well spaced from the electronics because acrylic is prone to static discharge. I also applied an anti-static solution to both sides of all the acrylic surfaces to reduce that risk a little bit, but the main protection is that it's well spaced. This should look beautiful in the Dutch Home Computer Museum. But there are other changes. Now, when I turn the system on, when I throw the switch, as you see there, look what happens. It immediately starts a blinking lights demo that it loads up from the microSD card. So you don't even need to connect it to a terminal anymore to see the blinking light. You just turn the system on and they immediately come online, which is handy for the museum. Now the system tells you what it's doing. When you turn it on, which I'm showing you again, the welcome message tells you that it has loaded the blinking lights demo from the microSD card and it's executing it. And if you press any key, it stops, you see? And then you have the system under your control again. It doesn't keep on doing the demo. Now there are new instructions added. The help file shows them. One of them is demo. It's one of the monitor instructions. You just saw what it does. The other one is walk. Right on top of demo, there is a walk, which is like run, but it uses a much lower clock frequency of only 10 Hertz. So you can run or you can walk your code and see the LEDs blinking accordingly. That's the other instruction added. Now, if you do a dir to the microSD card, you see that the demo.bin is there. It's a binary file. I added all the binary files to the GitHub repository, so you can find it all there already in binary. And if you run demo, the demo starts again. You don't need to switch the system on and off. Now, of course, I needed to update the firmware for this. I will show it to you. But before that, I need to show you a final bonus update to the instruction set architecture. It improved things a little bit. So this is the final update. All right, let's have first a look at the instruction set update. The first thing I did, you might recall if we go down the whole thing, that these two instructions here that have to do with the mail flag, one to clear the incoming mail flag and the other one to set the outgoing mail flag. Before, they were the last two instructions. So they were all the way down here after the conditional branches. I moved them up before the conditional branches. And the reason for that has to do with eventually doing an FPGA implementation of this processor. Because the way it is now, the way you see it here, if you look at these opcodes here, for the conditional branches, we have the non-conditional jump in here, and then immediately afterwards, the conditional branches start. And you can look at the two highest order bits of the opcode, and they are both 1 and 1 for all the conditional branches, all the way to the end. Not only that, only the conditional branches have opcodes which start with 1, 1. Everything else does not have 1, 1 in the two highest, most significant bits of the opcode. And what this allows me to do is when I do an FPGA implementation of this core, I do not need to use 256 addresses in the decoding memories for every instruction, because the reason we have 256 addresses for every instruction is that there are 8 flags. And for the conditional branches, we need to do a different thing depending on how those flags are set. Therefore, those flags need to identify different addresses in the decoding memories. But that is only so for the conditional branches. Those are the only instructions where we need to look at the flags. The other instructions don't look at the flags. So by encoding things this way, I can use a simple and single AND gate with 2 inputs to check if the 2 highest order or the 2 most significant bits of the opcode in question are 1, 1. I just do an AND of the 2. If the outcome of the AND is a 1, then I know I have a conditional branch. And then I know I need to look at the flags. I may need some extra logic to look at the flags instead of wasting 255 addresses for every instruction. And if the outcome of the AND is a 0, then I know that I am not with a conditional branch in hand. So I don't need to look at the flags anyway, and I can use only 1 address of decoding memory for all the other instructions. Probably I can also use only 1 address for the conditional branches, but then I need to know that they are a conditional branch so I can apply extra logic to look at the flags. Or I may just expand everything into 256 addresses, but only for the conditional branches then, not for all the other instructions. Now, in an FPGA implementation, this is important because the decoding memories will be using the embedded memory of the FPGA, which may not be a lot. In the case of Talos ES, that's completely irrelevant because I cannot buy small memories of, I don't know, 16K, 2K. I cannot buy flash memories that small these days anyway. I have to buy a larger memory, which in any case costs me like €2.5. So if I am forced to buy larger memories, I might as well use those extra addresses in a completely suboptimal way, which is what I am doing in Talos ES. And I will be doing the same in Talos CR, the single board version, which also uses DIP chips for the decoding memories, flash chips. But when I do it one day, if and when I do an FPGA implementation, I want to have an option in the way the instructions are encoded to not need to be so wasteful regarding memory. So I can use some smart logic to do that. And it doesn't get any smarter than having a single 2-input AND gate to know if I need to look at the flags or not. So that's the first change. Another change was I removed some redundancies. If I go here, back up, and you see instructions like this, A equals R and B equals R. These are identical. This is a 16-bit register-to-register operation in which I get the contents of register R and copy them into register A, and here the same, but for register B. Before I had these, at least this first instruction, I had it there, but I also had A high equals R high in parallel with A low equals R low. Well, that's exactly the same thing as A equals R. Same thing for B equals R. I also had B high equals R high and B low equals R low. Well, that's the same thing as B equals R. So I decided to remove the redundancies, leave the assembler. I didn't implement it. I hope the community will do that once I send out the Talos CR boards. But the community can come up with an assembler that has pseudo instructions, and we'll know that A high equals R high in parallel with A low equals R low is the same thing as A equals R, and therefore can accept both. But in both cases, use the same opcode. There are many other pseudo instructions that can be thought. For instance, here you have 2 parallel operations. The first is a memory operation and an increment operation. They are in the following order here, first memory and then the increment. And the current bare bones assembler requires that the order be this when you write the code. But of course, if you write the memory increment first and the memory access second, it's the same thing, but the assembler right now doesn't recognize it. So this is another type of pseudo instruction in which people can implement the code to be smart enough to disregard the order and know that we are always talking about the same opcode regardless of the order. And even more pseudo instructions, like there could be a pseudo instruction for a multiply operation, like A times B or whatever, because we have code for the multiply. So the assembler could replace that pseudo instruction with the appropriate code under the appropriate conditions. So these are examples of what the assembler could do. But for now, I just removed the redundancies related to this. I think there was one more redundancy, and I added some other instructions using the extra opcode space that I thought could be used. For instance, this parallel increment of both pointers to memory, incrementing them both at the same time, as opposed to one at a time. So I added this, and I think I added a couple of other things that made sense using the opcode space that was made available when I removed the redundancies. So that's basically it. These are the changes. I regenerated the binaries for the decoding memories. Everything's already updated in the repository. Everything I'll be talking about today has been in the repository now for 1 or 2 weeks, maybe more than a couple of weeks. So the repository is up to date with everything I'm saying. And of course, now that we have different instructions, I need to update the firmware as well, which I did. I'm using the version that you can find on the GitHub repository. That's just the Talos ES GitHub repository. I've given this link several times, but I'll put it down again in the video's description. If you go there and you click on firmware, and then you click on the .ino, which is an Arduino file. The firmware resides in the I/O controller, which is programmed in C from the Arduino IDE. This is the Arduino sketch. And the changes, let me show you first the change to the way the assembler works. This string here, the opcode table, contains the syntax of the mnemonics that are recognized. In other words, the way you write the code. And now I've removed some of those redundant instructions and changed the order because the order in which they are written determines the opcode corresponding to each of these instructions. So this has been changed accordingly to the changes I just explained with the instruction set spreadsheet. And then I took the opportunity and I made some other changes as well and added some functionality that was useful. For instance, if you look here, this is the setup. So this is executed only once. And at the end of the setup, you're used to this, you've seen this before, the welcome message. But now I'm adding something else. I'm checking if the microSD card is present, because I want to access the microSD card. And I do that when I call this new function called demo. In other words, the function demo is called on startup automatically by the new version of the firmware. And if we try to find where demo is, let's see, demo, let's check the next one. Here's the function demo, it's here. What it does is just loads an application that I already pre-programmed and I put in the microSD card. This application is basically just the Fibonacci series calculation that I have discussed in the previous episode, except that at the end I loop back to the beginning. So in the demo, a Fibonacci series is calculated ad infinitum in order to blink the LEDs. That's basically what it does. It will run the Fibonacci series infinite loop and blink the LEDs immediately upon startup. And the reason for that is in a museum setting, this system is going to the Dutch Home Computer Museum. What you want is that the museum employee comes in the morning and just switches Talos on, and the demo already starts, even without having to, get into a terminal or even connect a terminal to Talos. You just switch it on with the microSD card inserted, which it will be at all times, and it will blink the LEDs for the visitors to see. That's the idea. Now, after you load the demo, then I just take the system, I put the system in step mode, because to see the LEDs blinking, I cannot use the full clock speed of 4.6 megahertz. You will see nothing blinking. So I have to put it in step mode and generate the step clock pulses using the timer available in this microcontroller, and that's what you see here. If the serial port has nothing coming in other words, if the user didn't press any key, then these instructions here, they would just pulse the step clock from low to high and back to low with a delay of 50 milliseconds in between. So this is equivalent to, add 50 plus 50, so 100 milliseconds. That's the clock speed you get in the range of hertz. This is a couple of hertz, very slow. So you can see the LEDs blinking. Before we start pulsing the clock, the step clock, we will also, of course, take the CPU out of reset and out of halt, so the clocks are recognized and the demo application is actually run very slowly, but is actually run. And the moment the user presses a key, then this condition will not hold, and then we just halt the CPU, bring it to reset, and turn off the step mode. That's basically what this function is. Now, if I go back all the way to the beginning, we were here. There is something else I did, and let me just look for it. I implemented an extra instruction called walk. You see this in the help file, but I want to show you the actual instruction. So this is where the instruction is recognized. If the user types walk, then the instruction walk is executed. And then if we go to walk, here it is. That's the walk instruction. And you will see that it's very similar to what you saw for demo, except that it will execute whatever is in instruction memory, as opposed to loading the demo file from the micro SD card first. And instead of checking whether the user has pressed any key to post the clock, it will check the outgoing mail flag. Because if the outgoing mail flag is 1, then we know the program execution has been completed, and we bring the CPU out of execution mode. We halt it, we reset it, and we stop the step mode. And then we tell the user program execution completed. So essentially, walk is completely analogous to run. You would type run to execute the code in instruction memory at the full clock speed of 4.6 megahertz or whatever the user set with the dip switches. But with walk, instead of using the clock from the oscillator, this will be the clock. It will be the step clock. And again, we'll have only a couple of hertz clock speed. And the idea is you walk instead of run the code when you actually want to see the LEDs blinking. That's all there is to it. I may have made a couple of other cosmetic changes here and there, but essentially this is it. This is hopefully the final version of the firmware from me. I'm sure the community would do a lot better than this, but the final version from me is 25th of February 2024, and this is what is in the repository right now because I'm actually there. I am in the Talos ES repository. And with the system complete, it's going to its final destination, the Home Computer Museum in Helmond, south of the Netherlands. This is just half an hour from where I live, and I love this place. There are areas in this place dedicated to historically significant 1970s system, 1980s, 1990s, and the noughties. And this is the 1970s area, but Bart and I, the director of the museum, Bart, we were discussing where we should best put Talos. And we figured we would put it in the 1980s area right next to the Acorn Archimedes that you see there. The Archimedes was the first home computer system to have the first affordable home computer system to have a RISC processor. In that case, an ARM, and you're probably using an ARM processor right now to watch this video. But we thought, the first affordable RISC computer is so significant, and then we could put Talos that illustrates the internals of a RISC processor right next to it. So visitors can see the computer itself, the Archimedes, and then right next to it with the blinking lights show of Talos, see what happens inside a RISC CPU. Even if they don't understand it, they get an idea of the complexity of what's happening within that little black part, that epoxy part, the chip that they see in an Archimedes system. We thought this would be nicely educative, and it opens up a new dimension for the visitors of the museum. It's not only the outside of the system that they can appreciate, but the computations, how things happen within the chips. And Talos is ideal for that. So here's a little test run before I put the transparent shell on top. Everything seems to be working fine. It survived transportation. And then my girlfriend decided to do some glamour shots of it. This is the second computer system my girlfriend, who is an artist, took an interest on. Her first love was the Wang. She thought it had a very nice retro-futuristic aesthetics. And this because of the LEDs, of course. She finds it pretty cool. So here I am putting the transparent shell on top, trying to be very careful not to touch any of the boards. But I ended up touching the register file card and dislodging it from position a little bit. No big deal, but I am a perfectionist, so I didn't like that the card was pushed in a little bit. As you can see there, this card, the register file card, was slightly pushed in. So I decided to remove the case and correct it. I couldn't leave it like that, so here I go. Take the case off. And it's just a tick to put it back. There we go. Now it's good. So hopefully I can put the case back again without touching anything this time. I am using an anti-static set of gloves to prevent any, inducing any electrostatic charge on the acrylic of the case. And this is the final result. This is what it looks like in the 1980s area of the museum, blinking away to show visitors how a RISC CPU works from the inside. So yeah, that concludes it. Talos is in its home now. But before we end this series, just one more thing, one quick thing. A friend of mine, not on the internet, in real life, he asked me a question that is such a great question. It gives me an opportunity to go into more detail of a specific thing I did in the design, which I mentioned before in one of the earlier episodes, but this gives me a chance to show in practice, in real life, why I took that decision and what the implications are. So you've seen this slide before. I think in the previous episode, this is the code for the Fibonacci series calculation that I discussed in the previous episode. And this is the core loop. It goes back from here and then traverses this. So this is the core of the calculation. There is a jump on not zero flag low, and this is in the delay slot. So this is the loop. That's what you get. And during my explanation, I mentioned the following. Here we have an update of A high, which is this register, with the value in result high, which is this register. So this value goes there. Same thing for A low and result low. So this value goes there. In fact, these two operations, they are now not legal because this is actually just A equals R. That's what this is. There is no point in writing it down as two 8-bit operations. Now, the assembler, when the community works on the assembler, this can be added as a pseudo instruction, this part here. But right now, I changed the code. I'm using the old version of the code because that's what I showed last time. So here, the value of A high is updated with the result. This goes there. And then I told you that here, the new value of RH, because remember, this is always an addition and this is always a subtraction. So the moment I update A high, this new value of A high will percolate through the adder and update the value of RH or R high. So I mentioned to you that this is a memory write here. So the value that will be written in memory in the address pointed by the contents of address register 2 or AR2 will be the updated value of RH, not the value that was here. And this friend of mine, his question was the following, and I'll convince you that he must be right, and then I'll tell you why he's not right. His comment was the following: registers are updated in the rising edge of the clock. So if this is the clock, this is a rising edge, this is a rising edge, and this entire thing here is one clock cycle. So one clock cycle. So A high gets updated, say, on this rising edge here. Let me clear this. So on this rising edge, A high gets updated with the value in R high. And then we will have a falling edge, which will update the control signals. And then on the next rising edge, the memory operation will be done. But the value in R high will also itself only be updated here in the next rising edge. So what we will write to memory, according to my friend, is the previous value of R high, not the new one. So we will write the same value twice in memory, which is not what the result was. And his question is, how can this be? Now, where is he correct? He is correct that register values are updated only in the rising edges of the clock. That is correct. So on this first rising edge, A high will be updated, and only and of course RH, it will be updated with the same value it had before, because only now I'm updating one of the operands, and then the value in R high will be updated only here. But it is the new value that will be written to memory, data memory, in the address pointed by the contents of AR2 nonetheless. Why? The reason for that, if we go back to, let me change the slide. This is part of the schematics of the control card. It deals with the read and write strobe. So the read strobe, this is what comes out of the decoding memory, and write is what comes out of the decoding memory. Both are active high, because from the point of view of the decoding memories, all values have to be active high. And it has to do with NOP generation and reset condition. We discussed this in previous episodes. But notice that although the read value is just, this is a 7400, so NAND gates. So the read value is NANDed with itself, which means that the result will be just the negated version of the read value, producing the active low and read signal. This is what the memory sees. But in the case of the write strobe coming from the decoding memories, I am NANDing it with the clock, not with itself. Now, this is a NAND gate, so it's an AND with a little circle to invert the value. And write, which is what the decoding memory sees, is active low. So to prevent confusion, let's forget that it's active low, and therefore let's forget that this is an AND and pretend that it's just a vanilla AND gate. So what I'm doing, I'm ending the write strobe with the clock. So the write strobe will only kick in when the clock is positive. Otherwise, it will be masked away by the clock. You know, the result of an AND gate is only 1 if both inputs are 1. So both the clock and write have to be 1. Otherwise, the output is 0. And then it's inverted, and then we get a 1, which means that there is no write strobe, because the real write strobe is active low. But we can forget about that. So when will we get an actual write strobe? Well, only after a positive clock transition, when the clock is high. When there is a falling edge of the clock, what we will get is this here will become 1. But the clock will still be 0. So we will have to wait throughout this interval here, half a clock cycle, until the clock becomes 1. And then because the control signals will only change again here in the next falling edge, during this period here, we will actually have the right strobe active. And what this means is that on this rising edge of the clock, the value of RH will be latched, so RH will be updated, and then immediately the right strobe will kick in. So what we will write to memory is the updated value of RH, because the write to memory happens here, and during this part here, we were just masking the right strobe with this AND gate here. Now, why did I do this? Is the motivation for me to have done this to be able to use the updated value of the result register in a memory write operation? No, that was not the motivation. This is just a nice bonus. The motivation for masking the write signal is different. It is the following. This is the address. So the contents of address register 2 are the addressing memory where we want to do a write and put the contents of result high in that address. I have to make sure that the address is stable before I activate the write strobe. Because unlike a read, if you read too early, no problem, the wrong result that you read from the wrong address will be overwritten once the address value stabilizes anyway, so no problem. But if you write to the wrong address, then you will not overwrite that afterwards and make it correct, because you don't even know to which address you wrote. If this value is unstable, if it is changing while you are already in the right strobe, you may write to one or more wrong addresses, the wrong value, and then everything is wrong. So to prevent this and make sure that the contents of the address register are stable, I wait through this NAND gate here, I wait for half a clock cycle before I activate the write strobe. In other words, if the control signals are activated here, I will actually only write from this point on until here, during this period here. And this interval here makes sure that the address is stable. In this case, it's not too important because I updated AR2 here, then there is still another instruction in between, and I'm only using AR2 here, so it's already stable anyway. And I wrote it this way to give me even more room for maneuver. But there is a new instruction now, which is AR1++ together with AR2++. So I could have done AR2++ here in the previous cycle. So doing what I did, make sure that the update of AR2 is fully complete before the write strobe is activated from the point of view of the memory, so I don't write anything in the wrong address and then lose track of what happened. Now, having done this, it also gives me the opportunity to immediately use the updated value in this register, because I know I will have to wait half a clock cycle before activating the write strobe anyway. So when this rising edge kicks in and the register high here latches the new value, only then the write strobe kicks in, so I will already write to memory the updated value corresponding to the update of the operand A high. That's the thing, you see? Now, the only implication of this is that if this is one full clock cycle, the write strobe kicks in halfway. So we have to make sure that the memory access time is shorter than half a clock cycle of Talos. Not one clock cycle, but half a clock cycle. Because after this half, on the falling edge, I already updated the control signals again, and the write strobe will go away. I'll be doing something else. Now, is this a problem? No, it's not a problem, because the very point of Talos doing 5 operations in parallel every single cycle is to trade off clock speed for parallelism, because that's much more efficient. It saves power. It's better to do more things in parallel at a slower clock than to do things in sequence at a higher clock. It dissipates less power. And we have some limitations for the clock speed of Talos anyway. For instance, if you are using the ALU in 16-bit mode, then the propagation delay from the least significant bit here to the most significant bit there, that determines your clock speed. And it's a pretty high propagation delay anyway, unless you go for a custom ASIC to do this, which maybe one day, but right now, even in an FPGA implementation, there will be quite a bit of propagation delay here. And not only that, if we go here, that's the addressing logic schematics. So this is AR2. While we are counting and incrementing AR2 only for the least significant bits, say here, the first 4 least significant bits, then the propagation delay from the first to the 4th bits of this address counter is very short. So we are running Talos now at 4.6 megahertz, and it works. But if we were counting on the higher end of the address space, now the propagation delay is from the least significant bit to the most significant bit over here. And that's much higher. For all I know, it wouldn't even run at 4.6 megahertz if I were counting on the higher end of the address space. I'm only counting on the lower end right now. So even the 4.6 megahertz may not be reachable. I didn't calculate it because Talos ES and Talos CR, the new one, the single board one, are not made for speed anyway. As you saw, the demo is running at 10 hertz, because anything faster than that, then you don't really see the LEDs blinking. So the clock speed is not the point for these two computers. But when I do an FPGA implementation, then I will make a complete timing model of all the propagation delays, because then it doesn't matter. You can't see what's going on anyway. You want performance out of it, and then it does matter. But in any case, even in an FPGA, there are these bottlenecks, this long propagation delay here. You have the propagation delay in the ALU. And you have the decoding memory access times. Those are flash memories. Access times are 70 nanoseconds. Now that's a lot. That's a lot of access time, and you have to add that to this propagation delay here and to the propagation delay here. So there is only so much you can do to increase the clock speed. It's better business to, as I explained, use half clock cycle for memory access, because an SRAM memory access, even a cheap one, 25 nanoseconds, it's your right access to SRAM. It can be less than that. It can be 5 nanoseconds, 10 nanoseconds for more expensive memories. But 25 is plenty. So for this to become a bottleneck for me, then the total clock cycle for Talos would have to be only 50 nanoseconds. That's more than 10 megahertz. Forget it. It makes no sense. So the way I'm doing it, I think, is sensible. The right pulse, the right strobe kicks in here and has half a clock cycle. And this allows me to use the updated value of the registers when I am doing a write to memory. So this is it, folks. I hope you've enjoyed it as much as I've enjoyed creating this series. And I will see you next time with the continuation of the Cerberus 2100 series and the beginning of the Talos CR series. So stay tuned. Take care.